Welcome back to part 2 of our modelling with GeoGebra. So the next part of this process, we're going to have to put some points to mark the trajectory here of this stream of water. So I'll go back to my Tools menu and I'll select Points. Now I'm using the mouse wheel to zoom in as close as I can, and I'm going to have to just estimate the best spot and then a left click to place a point. I'll move across and do another one. Now don't worry if they're a little bit off as we're doing it at this stage. We can adjust them. I'm going to try to get the very highest point there, but I'm not exactly certain that I've got the very highest point. Just zoom back a bit, grab the, no, made a mistake, I'm still using points there, aren't I? So I'll get the moving tool and put that point up there somewhere, and now these last few I'll get in nice and close. And how many have I got? Is that about 10? That's enough. So I'll go to the moving tool, move across, and I'll zoom in nice and close and see that I'm happy. So I think I'll just move that. It's clicking onto the corner of the grid, so I'll just put that one. It doesn't matter if it's not on the y-axis. I'll put that one there. So I've zoomed out a bit, and now I'm zooming in with the mouse nearby. So look, I've gone a bit too far there. The image is pixelating so much I can barely see what's going on. That one seems all right. And so we just go backwards and forwards like that, checking each one as we go. So I'll pretend I've checked each one and I'm happy with all of those. Now, how do we get GeoGebra to create a mathematical equation? Well, there's many different ways we could do this. One of the aspects of your assignment task is to use technology to do this. Notice that in this list of objects, point A, B, C and D are not really the points we're interested in. A and B were the handles for the image, and point C and D were what I was using as I did the scaling. I don't even need point C and D to be visible anymore, and I don't need the distance to be visible anymore either. I haven't deleted it, but I've just hidden it from view. But it's really only these points that matter. So there's a convenient way to treat all of them as a single object, and that is to create a list. I'm just going to call it list 1, and we use curly brackets just like set notation. And what do we got? F, G, sorry, H, oh, can't type today, I, J, K, L, M, N. So I've just pressed enter there, so I've now got a list of all of those. Every single object in the list is points. While I'm here, notice how GeoGebra defaults to a very, very large number of decimals. I'm going to go to the settings cog and then open settings, once again the cog, and I'm just going to, for convenience, reduce that back to 3 decimal places on display. The computer will still remember all of the accuracy, it's just easier to read. And we can see here that this list is, that's the first point. Point E is those coordinates, and they're all now in one object. Now how do we get ourselves a function? Well, f of x equals, and there's a command called fitpoly. It means fit polynomial. If you're interested to know, you can hover here, and you can see that the first option is we give it a list of points and then the degree of the polynomial. So the list is L1. Now at the moment, it's trying, because there are 10 points, it's trying to fit a 9th degree polynomial, which is going to touch every single point. But of course, that's a ridiculous model. That's overfitted, because water doesn't have this little bump here, and it certainly doesn't come shooting down from above. So we will complete this formula down here by putting a 2 to force GeoGebra to use a quadratic or a 2nd degree polynomial model. Now that's my model. That's That's the quadratic formula there that does the best job of going as close as possible to all of those points. And really, that's the main part of what we want GeoGebra to do for us. Of course, we could do our own calculation. We could use this to verify our own calculations. But there's a few other little things that we could try to do. For instance, if I wanted to know how far from the starting point that the jet of water has landed, then I can click on this point here, and it tells me that the root of this equation, in other words, the place where the quadratic crosses the x-axis, is 1.77 meters. If I click on the model again, then there is a point just up here. Now I'm not talking about point I, I'm talking about this point here, which is the maximum, which of course you could determine from the polynomial once you had the polynomial. So it seems like the water gets a maximum of about 0.75 meters above ground level, even though you can see the stream of water is there. Now, that's the other point. The polynomial is as close as it can be, but it may not even be touching any of these points. So we can calculate the coefficient of determination. The formula is r square. We need to give the formula the list of points that we're looking for and the model, and 0.999 is a very high degree for a coefficient of determination, so that means the model is doing a good job of matching. And the last thing we might want to do is a residual plot. So a residual plot, we need a list of points and then a function. So let's just click on that. The list of points is L1 and the function is f. Now the residual point are these green dots down here. Let's zoom up a bit. The residuals should be close to zero. Residuals are the differences between the points and the model, the vertical distances. And they should be randomly scattered, so there should be no obvious pattern. And with only 10 of them, well, that's fairly, it's not like it's a wave or it's not like it's a curve. So there's a few above and a few below and they're all very close. So that residual plot indicates that a quadratic model is actually doing a good job. And really, that's about it for part 2. So thanks for watching.